that we're interested in this in the solution manifold of this nonlinear parabolic PDE, which is driven by white noise, which we have to regularize, and therefore we have to introduce a counter term, and we want to find a good understanding of this solution manifold. That's the goal of what we're doing, and in particular we want to show that we can choose this counter term in such a way that as rho goes to rho goes to zero, this regularization parameter goes to zero, in such a way that the solution manifold converges to a limit. And we wanted to do so in terms of a parametrization. So a map from lambda and P was, so let me write it like this. So this is R cross analytic functions. This is where lambda and P sits into phi. So we want to capture the solution manifold by parametrization. So you should think about it. You're in function space. And this is your infinite dimensional nonlinear manifold, which is infinite dimensional, but still it's a very thin set in the space of all functions. And you want to find we seek a good description, in fact, a low complexity description of this solution manifold, of this nonlinear manifold, which is stable under letting this regularization go to zero. And one way of interpreting what regularity structures is doing, or what we're doing here, is that this is possible, which is a bit surprising, because if you can take a very rough right-hand side, of course, there should be a price to pay, in the sense that you can no longer approximate your solutions in a good way. Like, that's the typical paradigm of numerical analysis. You need smoothness to be able to approximate your objects well. But regularity structures, in a certain sense, work their way around this. You still achieve a pretty low complexity description of your solutions. But this is not because and the reason for this is that you're not considering any type of right-hand side, but you're taking them from an ensemble which has good structural properties like stationarity, parity, reflection symmetry, and in fact scaling, which I will come back to in a second, or in a couple of minutes. So that's the idea. I think even if you're not interested in specifically interested in stochastic partial differential equations, you could be interested in this because it's also a way of kind of finding a sparse and efficient description of a high-dimensional object, which is this solution manifold. Okay, and so the idea was, so let's say this here is perhaps the solution manifold for lambda equal to 1, and the idea was to say, well, in the case when lambda is equal to 0, we know that the solution manifold is an affine space. That one we know how to parametrize. In fact, it's in a certain sense, once we choose an origin here, which we call pi 0, once we choose an origin here, we can write any other solution as pi 0 plus p, where p is from this space of analytic functions. And now we imagine, or we seek kind of a deformation of this kind of trivial parametrization in the linear case to the nonlinear case. And the way the ansatz we made was a power series ansatz. So the ansatz was that we said, let's write our solution. So, I mean, the first part of the ansatz was not particularly surprising. Let's write the counter term as a power series in terms of the lambda with coefficients ck. And the second part of the ansatz was much more interesting, namely let's write the solution, or this map we're interested in terms as a formal power series over all multi-indices beta of the monomial beta lambda p times kind of space-time, random space-time functions. And so Z beta was Z3, beta 3, the product over all n, d plus 1 Zn beta n, and Zn of p was just the nth entry in the power series representation you have for analytic functions. So dnp0, and Z3 was just trivial. Okay, so that was the ansatz we made. So we said, let's try to find this parametrization in a rather algebraic way. Instead of evoking nonlinear analysis, let's rather kind of bring in more algebraic concepts and to some extent also combinatorial ideas. And let's make this ansatz, and let's focus on these coefficients. Right? That was the idea, and we realized that a good way of thinking about these coefficients, in case of C, that's not so deep, as thinking of them as formal power series in the Z3 variable, and in case of these capital Pi's, as a formal power series in these infinitely many variables, which are given by these things here, with coefficients which have values in the random space-time functions. All right, that was the ansatz, and the nice thing was that there was a one-to-one translation of this PDE in this sense. So that was turning into L of pi is equal to pi minus, and pi minus is defined as Z3 times pi square plus C times pi plus psi times 1. That was that is what we saw last time. And then, so this was just, in a certain sense, a very compact notation for something that one should think of as being component-wise. This property here, beta 1, pi beta 2, pi beta 3, plus the sum over pi 1 plus pi 2 is equal to pi c beta, pi beta plus psi times the Kronecker symbol beta with the 0 index. And here the translation is that c beta is equal to ck if beta is equal to k times delta 3 and 0 else. And k has to be at least 1. And I put these constraints here because they're convenient. So beta 1 of 3 is not equal to 3, and beta of n is equal to 0 for all n. But that's just from this. And then I wrote down a couple of examples. of these components, and the goal was to show you that this was getting pretty complex. But there was one thing which is simple, namely because of this idea that for lambda equal to 0, we want to have kind of this pretty trivial parameterization. What's included, or what goes with this definition, is that the polynomials, the space-time polynomials, are contained. So that was the observation that if beta of 3 is equal to 0, but beta is not the 0 index, then this is equal to the space-time monomial xn if beta is del n and 0 else. And that was just a reflection of this idea, or this postulate, that we really want to deform the trivial situation, the trivial situation in the linear case into the nonlinear case. Okay, I think this is where we stop. Now the next thing I want to tell you, and perhaps then I take questions, is that the first thing we try to do is to do it in a sparse way. So we want to have, so I'm trying to use a little bit the language that might be dear to the statisticians. So the way we want to do that is, so we seek, in doing this, we seek maximal sparsity. And by this I mean that we want to minimize the set of all betas so that pi beta is populated. So we want to minimize the population. So sometimes this is called kind of population conditions. On pi beta and pi beta, well, drop the index, and that's section 7. Right, so in what I postulated here, we have it still does not kind of uniquely determine these coefficients, although we have this hierarchy of PDEs, and it does not determine these coefficients pi beta yet because of several reasons. And what I want to do in the sequel is kind of to come up with postulates or rules which eventually will fix everything. The pi betas, and in particular also the counter terms, the C betas. And the first step in doing so is to impose some sparsity. And that's what I want to explain now. But are there questions so far? That's good or bad? So, yes?
In the case where P0 doesn't exist, is it possible to construct P?
No, the P0 is very important. But in our case, it will exist. So we will always have a solution of this linear equation under the assumptions we'll eventually make. But even more importantly, we'll have a unique, we'll have a kind of canonical solution, right? So I think we as mathematicians, we're always used to be afraid, oh, but does the object exist? Here you should get in a different set of mind and rather think is it kind of canonical? Is it unique? That's actually the more important question here. And this affine space of solutions which you have in the linear case is clearly non-empty. And the more interesting question is there a singled out solution? Because this is how you start up building your coordinates. And that's something we'll have to come back to eventually, later on today. So the more important question is uniqueness, or the fact that you want something canonical, natural in the coordinates you're introducing. And that at this stage is not at all clear. Because this is an affine space. I could put the center of my world wherever I want, and every time I would get a new set of coordinates. And that's a little bit unsatisfactory, right? I want to have natural coordinates. But that can be done, and but we'll get to that later. More questions? Okay. So here comes the answer for the sparsity. So one can achieve the following. So achieve maximal sparsity, which is the following. So pi beta is equal to, well, this we already knew. It's over here, a polynomial. If beta is equal to the kind of basic multi-index, which puts a 1 on this space-time index and 0 elsewhere for some n. And it can be anything for something which I'm going to define, and it's 0 else. And that's, of course, the interesting thing, that it's 0 quite often. And I have to tell you what this beta is. So this beta is kind of a combinatorial expression in the multi-index, which is this expression here. So it takes twice the first entry of the multi-index, and then it subtracts the sum over all polynomial entries of the multi-index. And we can arrange so that this object only survives if this quantity is non-negative, which clearly is kind of a valuable restriction, because it tells you that only those multi-indices beta survive where, in a certain sense, the polynomial entries are somewhat balanced or counteracted by the first component. And there is a similar property for pi beta minus, and you find that in the notes. So that's the first convenient, or that's the first choice we can make. And the argument why you can assume that's kind of a little bit of a combinatorial inductive argument, which is based on the structure of pi minus and the fact that we only want to solve the equation up to analytic functions, which I forgot to write here. So in particular up to polynomials. That's how you get this. Perhaps I'm not going to show you the argument. It's nothing deep. It would be a good exercise, but I rather focus on something perhaps more important. Questions so far? Yes?
What does the star mean? What does the star mean in the definition of
It's anything. So when this condition is fulfilled, then pi beta is populated. Then it's non-zero.
So any function?
Any function, any random space-time function. X was the space of random space-time functions. Does that make sense? More questions?
Sorry,
Yes?
what is the bracket to the power of n?
This here?
Yeah, the bracket.
So this here is short for the function, for exactly this function. And that was short for the space-time monomial xi, ni, where n has the components n0 up to nd. But these things should also be explained in the notes. Or if they're not, please let me know. More questions? Yes?
Repeat the definition for the square bracket.
Sorry, can you?
The definition for the what are those terms?
Well, so a multi-index beta, so that's related to definition what a multi-index is. So that's a very important object here. So we're always in this ansatz which I raised, so let me put it here. So we want to define this parametrization of a general solution in terms of lambda and p, and that's a space-time function. And the ansatz we made was that this is a formal sum over multi-indices beta, and now I'm going to explain again what this is, over multi-indices beta of z beta lambda p pi beta of x. And what's a multi-index? That's something which you know from kind of plain multivariable analysis. When you take partial derivatives are indexed by multi-indices. And here we take partial derivatives with respect to these variables z3 and zn. So multi-index beta is something which goes from the disjoint union of 3 and n. So n was in n0d plus 2 and gives spits out a non-negative number in such a way that most of the arguments are equal to 0, in the sense that this here is a finite number. That's a multi-index. So beta will always denote a multi-index, right? So it's a frequency measure. It tells you how often do you fill up the 3, how often do you fill up the n's in here. And it comes up in the definition of the monomial. So that's the that's a big combinatorial object, which drives, which in a certain sense drives this ansatz. So it's a very important thing. More questions? Yes. First. Remy?
Just to know, would the definition of beta into brackets be different if we had a nonlinearity like the fifth power?
Very good. So this here is, the 2 is a 3 minus 1. If you had a quintic nonlinearity, it would be 5 minus 1. So it starts showing up in a certain sense the structure. So in general, what we're doing, or what one's doing in regularity structures, is more and more forgetting the equation and extracting structure out of the equation. And for instance, the power which appears in the nonlinearity in the end only shows up in a few places. It's in a few but significant places, and one place is here. There was a question, yeah?
So this sparsity, does it come, like we want to achieve this sparsity, does it come at some cost on, let's say, the regularization thing?
This is a sparsity that's uniform in the regularization parameter. It doesn't depend on the value. It survives even in the limit when you let the regularization parameter go to 0. That's actually important. It's more of an algebraic sparsity, which indeed, as we just said, is related to the structure of the equation. If you have a different nonlinearity, then you have more populated multi-indices, and the fact that you have a cubic nonlinearity leads to this population condition. So I mean, when I'm using sparsity, I'm doing that in order to tease you, right? To get the applied people interested. You should take it with a grain of salt. It's not sparse, I mean, we're not doing numerical analysis or approximation theory in the usual sense. In fact, in regularity structures, you will never see the word sparsity, but the jargon which is used is population. Something's populated or not. But it's really that. I mean, you want to. Still, I think the thought is the same. You want to find a representation of your manifold that's sparse, that in a certain sense is encoded in the least possible amount of information. And the first thing is that you want to say that this is an infinite sum. There is no, that has to be the case, but at least you want it to be somewhat sparse as an infinite sum. And that's the first step in that direction. More questions? Okay, so now comes perhaps the most important thing, namely we're going to go back to the scaling. And oops, I'm going to erase this. Because the biggest problem with the uniqueness, with the fact that we want to have something canonical, is that we cannot invert the L, because the rule of our game is don't impose initial boundary conditions. That doesn't make sense. So we need to find a different way of uniquely inverting the L, and that will be based on homogeneity in terms of scaling. And for the PDE experts, it will relate to Liouville principles. But you don't have to know that to appreciate this. So let's start with the scaling. So that's resuming a discussion we had on the first day, namely that there is a scale invariance of the solution manifold. And so let me motivate this by the following. So we already saw that white noise satisfied this scale invariance in law, where, let me put this somewhere, R was this parabolic rescaling operator we had seen in the first session. So so white noise had this very crucial scaling invariance in law, which brought up the effective or parabolic dimension, which was the I like to write it the other way around, which was the effective dimension of time, which was twice because of the parabolic nature, and each of the space dimensions has just weight 1. And in fact, as you will see, it's good to relax this, make this a little bit more flexible by looking at introducing an additional exponent s here, allowing for some flexibility. So suppose, so eventually we are interested in ensembles, noise ensembles, with the scaling symmetry in law which is given by this expression for some parameter s. So if s is positive, this field will be more regular than white noise. If s is negative, it will be rougher than white noise. So it's kind of an additional parameter I now introduce into the problem. Of course, in physics, you're mostly interested by white noise. But as a mathematician, sometimes it's a good idea to embed your problem into a more general class of problems. And that's what I'm doing here now. And s equal to 0 corresponds to white noise, as I explained in 2 or 3. But forget about this for a moment. and return to the solution manifold. And let's just, inspired by this here, introduce kind of a rescaling of the right-hand side, which now, we don't have yet to think about it as being random. So I want to define it in such a way that if we had this scale invariance in law, the transformation would keep it invariant. So I write S minus this exponent psi r dot. So this is this type of blow up. So it's a transformation on the right-hand sides, and you should think of it as being a blow up or zoom in. Yeah. Of course, I can define something like this. And now I want to ask the question: how do I have to transform a given solution so that what is the exponent I have to put here so that this phi hat has a chance of being a solution again? And perhaps not so surprisingly, you should see again this exponent, but then it should be more regular. Because we're inverting the heat operator, and that gives 2 digits of additional regularity. So that's the natural ansatz we should make. Now also for the counter term, we should make a corresponding ansatz, and that would be the same square here, h r square, h hat is equal to r squared times h. And but now comes perhaps the more important thing, because we also have to rescale the equation. We have to make sure that the nonlinearity. Let's write the equation again. Let me forget about the affine function. We have to make sure that the nonlinearity, which is cube, not square, is okay, and that requires a transformation of the lambda. So then this defines another solution, provided we also change lambda. So lambda hat has to be something in terms of lambda, and what we have to do is because of the cube, we have to compensate 2 factors of this, but then we also have to compensate in a certain three factors of this, because that's the difference between these two. And so what that gives you is 2 times 3 plus s minus d over 2. So that's a little calculation, but nothing deep. And we also have to redefine our convolution parameter, which I forgot to write here. So this is an observation, kind of a very typical PDE observation, that your equation, your PDE, has a certain scale invariance. It's a little bit different from the usual PDE point of view, because from a usual PDE point of view, you would say, well, there are too many terms, I don't have a scale invariance anymore. But since you allow yourself to adjust the parameter in front of the nonlinearity, you gain it again, you kind of in this extended sense. And so that's an easy but very important observation, because that will lead up to the definition of the homogeneity of a multi-index. And why is that so? Remember that our task is still to define these objects here in a canonical way. And so that means we have to impose constraints. And now in view of the scale invariance, we should impose the constraint that our parameterization in a certain sense is covariant or respects that scale invariance. Yes?
The definition of H hats,
Yeah?
we are used to write H of rho, and so it is H of rho,
Hat.
yes, rho hats, and
Yeah, and so everything has to be adjusted. The strength of the nonlinearity, the scale of the convolution, in a certain sense, everything has to be adjusted so that the quantities with the hatted quantities, again satisfy the same equation. And a simple, simple, stupid calculation shows that this is the case, provided I do it like this. And eventually we'll draw some information, important information out of these exponents which show up here, as we will see. Okay, so the postulate now is that that our parametrization should be compatible, should respect this scale invariance. Right? We want to find a canonical way of parameterizing the solution manifold. So the solution manifold has a certain symmetry, but our parameterization is better compatible with this symmetry. So what does that mean? So that means if the parameters lambda, p, and psi give rise to phi and h, then this should imply that the new set of parameters, lambda hat, p hat, which I haven't defined yet, psi hat, should give rise to phi hat, h hat. So in a certain sense, so there should be this compatibility of our parameterization of this object here with the scale invariance. But I haven't told you what p hat is, so let me do this now. So p hat, in view of this picture which I erased, should be transformed as phi hat, as phi. So p should transform as phi. Why? Because there was this, you should always have this picture here in mind. So this is pi 0. This here is a point pi 0 plus p. And we want to lift this parameterization. So in the linear case, we wrote phi is this fixed, this distinguished solution plus p. So p should transform like phi. So this should go alongside with the condition that pi hat is defined in the same way as phi. So pi hat arises from phi in the same way as p hat arises from p in the same way as phi hat arose from phi, right? So that's a postulate. Now the question is, what does it mean in terms of the pi's, right? Right? Because in the end, those are the objects we're interested in. How does this postulate on this parameterization? How does it translate what does it mean on the level of the coefficients, right? And that's not so difficult. We just have to understand how the coordinates transform. And now, of course, everything is always erased. So let me remind you that the definition, there was this combinatorial factor, but essentially it was the partial derivative. So, so what is Zn of p hat? That's clearly related to Zn of p. And what we get is this length factor or rescaling factor r to the power n minus plus 2 minus s minus d over 2, where the norm of n, so to say, is 2 times n0 plus n1 plus nd. So we get this parabolic kind of way of measuring the size of a space-time multi-index. So this is just, you apply the chain rule, and for the Z3 variable, of course, this is even easier because Z3 of lambda was just kind of a dummy thing, so I just have to look at this prefactor here. Is equal to R 2 times 3 plus S minus D over 2 times Z3 of lambda. And now if you plug this in and you use this postulate, you get a condition of the coefficients. In German, I will always call this Koeffizientenvergleich, but I don't know what the is there a good French word when you say two polynomials are identical if their coefficients are identical? Anyway, so that's what this basic principle is exactly what we're now applying to this power series representation to infer how this should behave, and again, that's a completely elementary, in no means deep calculation from which you learn that the coefficients satisfy the following transformation rule. So we get that C beta hat is equal to R2 minus beta 3 times this exponent, 2 times 3 plus S minus D over 2 C beta. This is how in this easy series representation which I raised, so H rho is k larger than 0, larger than 1, C k Z3 k. So that's an easy thing, and then more interesting and more annoying to write down is the following: that pi beta rescales like r to some exponent, pi beta r dot, where beta, this exponent, is defined by the following expression. So beta minus 2 minus S minus D over 2 is equal to beta 3 times 2, 3 plus S minus D over 2 plus the sum over n, beta of n, n minus 2 minus S minus D over 2. So where the homogeneity norm of beta of multi-index is defined by this expression. So again, this is not really inspiring because you have to make sure that you don't make a mistake on the exponents, but it's absolutely crucial. This calculation is absolutely crucial because this exponent here will give us a lot of information. And in fact, a nice argument is that one also has a similar property for the right-hand side, which is the object which I always denoted with the superscript minus. And not surprisingly, the rule is beta minus 2 times pi beta minus r. So this minus 2 again comes just from the differential operator. Okay. So far, so good. I hope I didn't make a sign mistake. I think it's okay. No, I think I made a sign mistake. That should be a there should be a minus here. In the sense that a positive beta, a large beta, is good for regularity, and a negative beta is bad for regularity. So you should compare that to the noise rescaling, which was defined also with a minus. And so here there should be minus, and then here that also turns around. This is minus beta plus 2. I hope in the notes it's correct. Okay, so why is that important? Because that suggests that we should hope for a scale invariance in law, which will give us uniqueness. Are there questions so far? Yes?
So the scaling of the data of p hat is plus 2. So why in the next part it becomes minus?
Yes, so perhaps this is also wrong. Yes, indeed. That should be minus 2, and phi, probably I also wrote that wrong, minus 2 minus s minus d over 2. R phi hat. Thank you. So the problem is that at some point I turned this, so we started out, so that's always where I get confused myself. So we started out by considering an invariance in scaling, which was this one here, to which we will return. And now I said, okay, let's look at this object. Let's forget about the invariance of scaling, but let's look at the x at the hat, which kind of would be defined by this identity, which means I have to bring this on the other side. And then it acquires a minus sign. So therefore, it's good if I write it like this, because then the beta, the homogeneity of beta corresponds to a regularity exponent. Like in white noise, this number here, or in the generalized noise, corresponds to a regularity exponent. And if I get the sign wrong, then of course it's an irregularity exponent, and it wouldn't be consistent. More questions? Yeah.
That reminds me when you want to introduce the actual parameter s.
Where do you? Yeah. Okay. So I should remind you why.
Yeah, I'm just confused.
Okay. So there are several reasons. I mean, the official reason is we want to look at more general situations than just white noise. So we make our problem harder. The unofficial reason is for some specific PDE reason, we cannot treat white noise itself, and that will become apparent in the next section. So in fact, we have to choose S to be irrational. That will become apparent in the next section in order to have in order to be able to apply a certain uniqueness argument, which is a PDE uniqueness argument and which goes after the name of Liouville. So I hope that will become clearer next. But the official way is say, well, I mean, let's look at a more general problem. More questions? Okay. So now let's capitalize on this. What am I going to erase? This here. So that's section 10. Uniqueness of pi beta given pi beta minus via L of pi beta is equal to pi beta minus plus analytic. So again, we're looking for an algorithm to construct these coefficients, these pi betas, what Heira calls the model. So we want to be, we want to have something that is unique, exactly tells us what we have to do, an algorithm. And one problem we have is that we don't have so far a canonical way of solving this PDE because we don't impose any boundary conditions or initial conditions. And we don't want to do so because we want to capture all solutions. So we need to sidestep this. And the way to sidestep this is to exactly appeal to the scaling invariance, because what we learned from the two previous sections is that if indeed we start out with a noise which has this scaling invariance in law, then we should expect, or we should postulate, that in view of this line here, also the coefficients have a scale invariance in law. And now again, like here, the exponent turns around and becomes kind of more natural looking. So that's for beta, for pi, and the corresponding one for the right-hand side, the p beta minus. Right? So that is exactly a little bit like the argument which we used in section 2, that if we impose the scale invariance of the noise, and so this only makes sense in the limit when we let the regularization go to 0. It's natural to expect that the limiting model, the limiting coefficients, will inherit the scale invariance, but of course with an individual exponent which depends on the multi-index, and the expression is the one which I wrote down here. Yeah, so that's a natural postulate. And in particular, this suggests that if beta is positive, the homogeneity of beta is positive, we should have something which looks more like a function, although of low regularity, like Brownian motion. If the homogeneity of beta is negative, then it's definitely not a function, but a distribution, and it should be more like white noise. And of course, of varying degrees of regularity or irregularity, depending on the value of the homogeneity. Okay, so Now let's convert this observation into a postulate, another restriction we make on the model. And we don't want to make this restriction because this will only emerge in the limit of vanishing regularization. So we want to soften it. And we soften it as an inequality. So postulate, we want to suppose that if we look, let's say, at the expectation of p beta, and we mollify it on scale 0, on scale r, and we look at the origin, I remind you what this is in a second, then, and we multiply it with r to the power minus the homogeneity of beta. So again, now we bring the exponent on the other side. Then the lim sup of this should be finite, small scales and large scales. And let me remind you that this was, in a certain sense, taking the pi beta and mollifying it, averaging it out with respect to our rescaled Schwarz function, 0 minus x. And psi r was always the same definition, was a Dirac sequence. Psi r of x is r minus d psi of r inverse x. So if this were true, then these expressions would in fact not depend on r. I don't want to impose this because that would something which I will not have in the limit as rho goes to 0, only in the limit when rho goes to 0. So I just impose it in this weaker sense as a way of vanishing at the origin at a certain order, or not blowing up too fast at the origin at a certain order, and at the same time a behavior at infinity. Questions? Yes?
Where do we impose the sparsity conditions?
We already did. So that was 3 sections before. So I imposed them, but I didn't tell you the argument why we can achieve them. That's in the notes. So we already did impose that. Now we impose something more. And we will impose a third thing. And then with these 3 postulates, there will be a unique set of coefficients. So we're on the way of of making this canonical choice of defining how we want to understand this, how we want to define this parametrization. So we're on a way of making educated postulates. I'm saying educated because in the end we of course have to show that we can achieve this. But so far it's more that we're optimistic and we make all these postulates and hope that they make the thing unique. That's what I want to convince you of. And then the hard work is to show that indeed these postulates can be fulfilled. And in fact, one gets also more quantitative estimates. This here denotes the expectation with respect to the ensemble. Of course. More questions? Yes?
There is one thing that I did not manage to read.
Yeah?
In the last but one line, psi r of what?
0, which is this point, which is the origin. 0 minus x. So that was the formal definition, since I want to at least allow myself to think of pi beta as being a distribution. Was this distribution applied to this mollifier? That was something we did on the first day. Yes?
Sorry, beta is a multi-descriptive function from n to the power d plus 1.
So beta is something which, so I give you, so beta, I mean all the information of beta is in these numbers. So for, this is one integer, and for every space-time index n, which was, n0, n1 up to nd, which is a space-time multi-index. So for every space-time multi-index n, it gives you a non-negative integer. That's what, so beta in a certain sense is a multi-index of a multi-index, to be very precise, because strictly speaking, this n is also a multi-index. N is kind of a space-time multi-index, and beta is a multi-index of a multi-index. But I will just use the language, beta is a multi-index. But you should, because that's really crucial. If it's not clear what the beta is, you should keep asking, also others.
I'm sorry, can I verify that when R go to 0, so beta will be go to almost 0 too?
No, beta is something fixed.
Yeah, beta times R. Because,
Where do you see beta times R?
in the lim sup.
Here you see R to the power minus the homogeneity of beta. The homogeneity was defined here, so the homogeneity, so think of, so this here is a map on multi-indices into the real numbers. It's evaluation on multi-indices, which is defined by this line. It looks like an ugly expression, but it's motivated, hardwired by the scaling properties of the equation. So there's no choice. That was a natural definition. And it's this natural number which appears here. So this is just 1 over r to the power beta.
I think that the one that's not here is the other one inside the expectation.
Here.
Yes.
That's defined here. So this was a notation which I introduced on the first day, which was that if I take a distribution and the index r is nothing else than, in a certain sense, the mollification of the convolution, the distribution around the point x on scale little r with help of this Schwarz function psi. Yeah, and I'm using this here with evaluated at the origin, and the origin is singled out because this is the point around which I do my scaling. So that's why something which otherwise might look strange, this is why you have the zeros sitting here, because that's the center of my scaling transformation. More questions? Yes?
This intuition, is that saying that pi beta is a function at 0, or is there another intuition behind that?
So I'm taking pi beta, which in the limit of vanishing regularization typically will be just a distribution. So I cannot even point evaluate it, but I can ask it a question once I convolve it. So I convolve it, and then I evaluate the convolution at the origin. But that, of course, just means I'm standing at the origin and I'm taking an average of the values around the origin. So I'm zooming into the origin because I let r go to 0, and I say that okay, if the homogeneity of beta is positive, this means this function has to vanish to order homogeneity of beta at the origin. But the homogeneity of beta can also be negative, and in relevant cases, there is something here. Probably again, this might be no, that's correct. This can be negative because you have a minus d over 2 here. Then, in fact, this is rather a condition which tells you, well, in fact, it blows up because it's a distribution which you cannot point evaluate, but it blows up in a controlled way. Yeah? And this condition is a condition on large scales. It tells you how large scale averages, how thermodynamic averages of this distribution behave. So here, if If beta is negative, then it's good because it tells you large-scale averages decay. And if beta is positive, it's bad, but still it tells you large-scale averages can at least not grow too fast. Yeah? More questions? Okay. So the main reason of writing, so on the one hand, so why I'm writing this, on the one hand, it's perfectly compatible with the emergence scaling I want to have if I let the regularization go to 0. And on the other hand, it guarantees uniqueness. And that's something which I would like to write down now. So the claim is that for any beta which satisfies our population condition and is not necessarily polynomial, so that was what I introduced a little bit earlier without giving you any proof, and given right-hand side pi beta minus, let's suppose I have constructed this, there exists at most one, well, in fact, there is an existence result, but the more important thing is the uniqueness, such that L of pi beta is equal to pi beta minus, plus I can allow for any polynomial of degree less or equal to the homogeneity of beta minus 2. And that's the parabolic degree. And for this to be true, now comes the main reason for, the main honest reason for introducing the S. That S is irrational. And this is a PDE statement which is in a certain sense connected to Liouville principle. And the reason why we need S irrational is, the only reason we need it is that these exponents which come up here are not integers for a populated beta. The only reason for kind of making this somewhat strange assumption that the level of regularity or the scaling is irrational is that it ensures that these exponents which come up here are not integers. And that is something we need for this PDE statement. Questions? Yes?
What do you mean by parabolic polynomial?
Sorry, it's not a parabolic polynomial, but it's a parabolic degree of, and I will explain what I mean by this. So I'm writing, what does it mean to be a polynomial? That means you can write it as a sum like this, and the degree of this polynomial is the maximal length of n such that an is not equal to 0. And I say parabolic because this here, remember, was twice times n0 plus n1 plus nd. So I see the parabolic structure of things in there. So this is why, but I will, mostly drop this because it's always implied. So again, the big issue with constructing the model is that in general, I cannot, I don't have a unique solution of this problem because the kernel of L is huge. the kernel of L consists of all analytic functions. So that would be extremely bad for my construction if at every step in this inductive procedure in building up the hierarchy, I would be completely free to choose this analytic function. Then, what do the coordinates mean if I cannot somehow have a good meaning? So for the better or the worse, I have to find a way of singling out a solution, of inverting this differential operator in a unique way. And again, the rule is there is no boundary, there's no initial layer, so all this is not allowed. So instead of doing this, I'm imposing, in a certain sense, a growth at infinity. So it's, if you want boundary conditions at infinity, which are expressed here, but at the same time, I also impose a vanishing condition at the origin. And that at first seems completely arbitrary, but I try to convince you in the section before that what I'm imposing here is, in a certain sense, targeted towards where I want to end up when I let the noise go to zero. So it's in a certain sense a consistent postulate. It's exactly in line with how I imagine the limiting model, the limiting description of my rough manifold to be. So, so in that sense, that's a natural thing to do. And now, in the notes, you will find kind of a nice, cute argument of this Liouville principle. But if you haven't seen it like this, it's not so hard to understand. So let's suppose you had two solutions of this equation. Then, of course, since this is a completely linear problem, you look at the difference. So the difference of the two solutions, let's call it f, essentially, let's be simple, solves this right-hand side 0. So then again, we know the f must be an analytic function, a random analytic function. So because of this condition, which tells you that this analytic function cannot grow too fast at infinity, it must be polynomial. And the degree of the polynomial must be less or equal to the length of beta, the homogeneity of beta. On the other hand, now comes this condition. It's less or equal to the homogeneity of beta, but that object is not an integer, so therefore it has to be strictly less than the homogeneity of beta. But then this first condition tells you that this polynomial has to be 0 because it vanishes to a higher degree at the origin. So these two conditions just fit together and kind of make that the kernel of this linear operator L on this space vanishes. And that's what kind of makes this construction unique. What really, that's the only way we can convert this into, if you want, an algorithm. Right. Yes?
Is this like almost sure, like for every realization of the noise?
Yes.
We get a high beta. Okay.
Yes. So this is always, in a certain sense, implied that this means almost surely. So we don't care for events which have 0 probability. More questions? So this is kind of a very convenient ordering principle in elliptic and parabolic PDEs. I mean, I know there are only very few people among you who are kind of have grown up with PDEs, but I know that there are some. And for those, I'm saying that that there is a way, Leon Simon did that, of deriving Schauder theory from Liouville principles. So Liouville principles are intimately, in a certain sense, are the pristine, the pure form of regularity theory. And so therefore, it's not so, since in the end, regularity structures is about regularity theory, it's not so surprising that at some point Liouville principles will do play a role. Okay, so far so good. There's a nice proof with a semi-group argument in the notes we're kind of proud of. And okay, so let me finish by two things. going to erase this. So we need one last postulate to make our construction, to really have an algorithm for the construction. And that last postulate has to do with the fact that we also want to impose something on the pi minus, which is so actually there is one chapter in between, one section in between, which means that where we restrict to the case of 4 space dimensions, and which means capital D is equal to 6 and S strictly between 0 and 1, and of course irrational. I get back to this later, but in order to finish the uniqueness, let me kind of tell you that there is still one task to do. Remember that in a certain sense the model is defined by solving this equation, and then there was an explicit formula for pi minus, but this here contained the term beta c beta 2 pi beta 1 plus and so on. So far we don't yet have uniqueness. We don't have yet an algorithm because we're still free to choose these constant c. And after all, these constant c's are extremely important because they tell us what the counter term should be, at least in this formal fashion, because the counter term, the ck's were just the coefficients in this formal power series expansion of the counter term. So, and in the end, that was, in a certain sense, the first primary task to identify the counter term. And so, if we don't see a way of how to choose these constants, we haven't finished our task. And so the last postulate you need to make in order to fix these constants is something very much in line with this condition here, just that you do it on the level of the pi minus. So last postulate is again a large scale condition, and here I have 2 minus beta. That's the 2 which is here. The expectation of the modulus of BR minus 0, the lim sup, stays bounded. So let me highlight kind of these three conditions we need in order to ensure that we have no degree of choice anymore, and that everything is fixed. And so we claim that this fixes the C's, provided we make a population, we constrain the population, provided, okay, for this audience, we make the sparsity assumption, postulate, or axiom, that ck vanishes unless s times k is less than 1. And k, of course, is not equal to 0, so it's a non-negative integer. So that's the population condition we need, unless S times K, S was the regularity parameter of the noise, unless S times K is strictly less than 1. All right, so Ck is equal to 0 unless S times K is 1. Okay. So that means at least if we truncate the sum at some level, in a certain sense, the leading order coefficients, which might be many if S is small, and that's in a certain sense the case we should aim at an S which is which is positive but very close to 0, then we have finitely, but quite a number of these counterterms, and they contain, in a certain sense, the essence of the renormalization. And the claim is, if we truncate this series in this sense here, so focus on just a finite number, then these are completely determined by the postulates I made. And this is something which is well known in physics. So before I say what's well known, let me say that this thing here we're actually going to use just in a single way. So we use star, which is this here, only in the following way. Only in the way of saying that the limit, if r goes to infinity, of the expectation of the right-hand side of the model averaged over this large scale, evaluated at 0, that this is equal to 0, provided the homogeneity of beta is less than 2. So the way this condition, which eventually we'll prove holds, and we will even prove that it holds up to any moment. But here, for the uniqueness, the only way we use this postulate, which was in line with the scaling, is in this sense, that some space-time average, ensemble and space-time averages vanishes. So in a certain sense, you may say that the constants in the counter term, or the coefficients in the counter terms, or the coefficients of the counter term are chosen such that certain ensemble, and in our case also space-time averages, vanish. And this is something, I'm just saying that, of course, it doesn't carry much information for most of you. This is something which goes under the name of a BPHZ type of renormalization. This is at least how this kind of, or choice of renormalization. Renormalization. This is the wording which is used in the regularity structures papers, and this stands for names Bogolyubov, Parzyuk, Hepp, Zimmermann, and which is kind of math physics literature, where they also use the same, morally speaking, the same type of principle of fixing the counter term by imposing that certain ensemble averages vanish. Okay, so I don't know whether it's reasonable to start to give the argument for this. If I start, let me perhaps kind of give you just this here, and then we postpone that to tomorrow. So let me just finish with section 11. I just wanted to do this now because now everything is in a certain sense the rules of the game are now clear. I exactly stated what I want to understand by a model. How I want to think about this renormalization. So let's go back to section 11. So what we're interested in is we seek a situation or a setting where on the one hand we're in the singular case, by which we mean that the solution of the linear equation, the pi 0, is not a function in the limit when the regularization goes to 0. That was what I said in the very first course, very first lecture. The interesting case is when the solution of the linear problem is not a function, or when no solution of the linear problem is a function, because if it's a function, we're in the classical setting, and we can kind of give a sense to the cube. And so therefore, it's not interesting unless pi 0 is a genuine distribution when we let the regularization go to 0. Now, if you look at this line here, or what I raised in terms of scaling law, this should be the case if the homogeneity of the 0 multi-index, so this just means the multi-index which associates 0 to everything. If the homogeneity of the 0 multi-index is less than 0. And I raised the formula for the homogeneity, but it's in the notes, and it's equivalent to saying that the expression 2 plus s minus d over 2, which we at some point called alpha if s was equal to 0, if this is negative. So on the one hand, we want the problem to be interesting, which means singular. And on the other hand, we want it to be treatable, which means renormalizable. And that means kind of a condition which goes in the opposite direction. And for this one, I want to remind you of the way the nonlinearity rescaled under blowup. So we had this exponent on the blackboard, 3 plus s minus d over 2 times lambda hat. So this is telling us how the other way around, how the effective strength of the nonlinearity changes as we zoom in. And the problem is only has a chance of being able to be treated by renormalization, at least by kind of the existing renormalization, if the strength of the nonlinearity goes to 0 as you zoom in. So the condition is that this here should be positive. So that means we get the condition that 3 plus s minus d over 2 must be positive. So that shows you that there is actually not such a huge range one can cover here. So it's just in terms of the regularity s of the noise, it's just a unit interval. So hence s has to be between d over 2 minus 3 and d over 2 minus 2. So, and therefore, it's just a convenient choice to say, because then sometimes there's a little bit less to write, to say that d is equal to 6 which means that the physical, I mean the space dimension is equal to 4, and then this condition turns into S is between 0 and 1. And that's the choice I'm going to make for this course. And in this case, the formula for the homogeneity also simplifies a bit, which is the last thing I'm going to write down. So in this case, beta minus alpha is equal to 2 times S beta 3 plus the sum over n beta n length of n minus alpha. And alpha is S minus 1, so that's a number between minus 1 and 0. Remember that we insisted on alpha being negative because the problem is not interesting otherwise. Okay, so let me stop here. In a certain sense, now we have exactly defined the algorithm by which we want to construct this parametrization of our nonlinear solution manifold. There is one other part of the story which I want to tell you, namely that now it looks wonderful. We have this parametrization, but what I have to convince you still of, or what I have to the kind of the caveat which I have to tell you tomorrow is that this parametrization unfortunately is not universal. It depends on the chosen base point, which means in order to be fair, we have to kind of give up of using the origin, which anyway has no meaning, as a base point, but we have to consider kind of all possible base points. And in order to do so, we have to be able to convert one parametrization into another. So we have, like in differential geometry, instead of having a single chart, we will have kind of infinitely many charts which are indexed by one space-time point, and we have to be thinking about changes of charts, changes of coordinates. And that gives rise to something which in regularity structures is called the structure group. That's a very deep, somewhat algebraic concept which tells you how this kind of change of base point works. So that's next to finishing paragraph 12 is what I have to tell you tomorrow. And next week I will start telling you, eventually the main deliverable is to estimate, to really construct and more importantly estimate this model uniformly in rho, and that's where Malliavin derivatives and Malliavin calculus will be very handy, but that I think will only start next week. Okay, so sorry for being a bit over time.